Offline. Goes who? Come on. Okay. That's so weird. Why does it say offline? I just reload. Hmm. Okay. There we go. Okay. See, so I'm a bit behind, but yeah. There we go. Okay. So I'm going to be reading about batch normalization, which I know bit behind, but I'm already familiar with it conceptually. I just want to read the original paper. So, batch normalization, accelerating deep network training by reducing internal covariate shift. Sergeyev and Christian Segedy. Abstract. Training deep neural networks is complicated by the fact that the distribution of each layer's inputs changes during training as the parameters of the previous layers change. This slows down the training by requiring lower learning rates and careful parameter initialization. It makes it notoriously hard to train models with saturating nonlinearities. We refer to this phenomenon as internal covariate shift and address the problem by normalizing layer inputs. Our method draws its strength from making normalization a part of the model architecture and performing the normalization for each training mini-batch. Batch normalization allows us to use much higher learning rates and be less careful about initialization. Now that's where it's coming from. It also acts as a regularizer, in some cases eliminating the need for dropout. Applied to a state-of-the-art image classification model, batch normalization achieves the same accuracy with 14 times fewer training steps and beats the original model by a significant margin. Using an ensemble of batch normalized networks, we improve upon the best published result on ImageNet classification, reaching 4.9% top 5 validation error and 4.8% test error, exceeding the accuracy of human raters. Cool. Number 1, introduction. Deep learning has dramatically advanced the state of the art in vision, speech, and many other areas. Stochastic gradient descent has proved to be an effective way of training deep networks in SGD variants such as momentum and Adagrad have been used to achieve state-of-the-art performance. SGD optimizes the parameters theta of the network so as to minimize the loss. Theta equals arcmin of theta 1 over n, sum of 1 to n of the loss of the input x and the original parameters theta, where x1 to n is the training data set. With SGD, the training proceeds in steps, and at each step we consider a mini-batch x1n m of size m. The mini-batch is used to approximate the gradient of the loss function with respect to the parameters by computing 1 over m, the partial derivative of the loss function with respect to the parameters. Using mini-batches of examples as opposed to one example at a time is helpful in several ways. First, the gradient of the loss function of the mini-batch is an estimate of the gradient of the training set, whose quality improves as the batch size increases. Second, computation over batch can be much more efficient than M computations for individual examples due to the parallelism afforded by the modern computing platforms. Computation over batch. While stochastic gradient is simple and effective, it requires careful tuning of the model hyperparameters, specifically the learning rate used in optimization, as well as the initial values for the model parameters. The training is complicated by the fact that the inputs to each layer are affected by the parameters of all preceding layers, so that small changes to the network parameters amplify as the network becomes deeper. The change in the distributions of layers inputs presents a problem because the change in the distributions of layers inputs presents a problem because the layers need to continuously adapt to the new distribution. When the input distribution to a learning system changes, it is said to experience covariate shift. Shimodaira 2000. This is typically handled via domain adaptation. However, the notion of covariate shift can be extended beyond the learning system as a whole to apply to its parts, such as a subnetwork or a layer. Consider the network computing loss equals F2 of F1 of U and theta 1 and theta 2, all of and theta 2, where F1 and F2 are arbitrary transformations and the parameters theta 1 and theta 2 are to be learned so as to minimize the loss L. Learning theta 2 can be viewed as if the inputs x equals F1 of U and theta 1 are fed into the subnetwork L loss equals F2 of x and theta 2. For example, a gradient descent step theta 2 assigned from theta 2 minus alpha over m training step size, or the learning rate over m multiplied by the sum, so that average over the partial derivatives of f2 with respect to the parameters. So the gradient, so the average gradient across the batches times the step size. So for batch size m and learning rate a, it's exactly equivalent to that for a standalone network f2 with input x. Therefore, the input distribution properties that make training more efficient, such as having the same distribution between the training and test data, apply to training the subnetwork as well. As such, it is advantageous for the distribution of x to remain fixed over time. Then, theta 2 does not have to readjust to compensate for the change in the distribution of x. Fixed distribution of inputs to a subnetwork would have positive consequences for the layers outside the subnetwork as well. Consider a layer with a sigmoid activation function, z equals g of wu plus b, where u is the layer input with weight matrix w, and bias vector b are the layer parameters to be learned, and g of x equals 1 over 1 plus exponent negative x. As magnitude of x increases, g prime of x tends to 0. This means that for all dimensions of x equals w times u plus b, except those with small absolute values, the gradient flowing down to u will vanish and the model will train slowly. However, since x is affected by w, b, and the parameters of all layers below, changes to those parameters during training will likely move many dimensions of x into the saturated regime of the nonlinearity and slow down the convergence. This effect is amplified as the network depth increases. In practice, the saturation problem and the resulting vanishing gradients are usually addressed by using rectified linear units. ReLU equals careful initialization. In practice, the saturation problem and resulting vanishing gradients are usually addressed by using rectified linear units, careful initialization, and small learning rates. I already know that. If, however, we could ensure that the distribution of nonlinearity inputs remains more stable as the network trains, then the optimizer would be less likely to get stuck in the saturated regime, and the training would accelerate. We could ensure distribution of nonlinear inputs remains more stable as the network trains. We refer to the change in the distribution of internal nodes of the network in the course of training as internal covariate shift. Eliminating it offers a promise of faster training. We propose a new mechanism, which we call batch normalization, that takes a step towards reducing internal covariate shift, and in doing so dramatically accelerates the training of deep neural nets. It accomplishes this via a normalization step that fixes the means and variances of layer inputs. Batch normalization also has a beneficial effect on the gradient flow through the network. By reducing the dependence of gradients on the scale of the parameters or of their initial values, this allows us to use much higher learning rates without the risk of divergence. Furthermore, batch normalization regularizes the model and reduces the need for dropout. Finally, batch normalization makes it possible to use saturating nonlinear areas by preventing the network from getting stuck in the saturated mode. Batch normalization. Use saturating knowledge by preventing networks stuck in the saturated modes. In section 4, we apply batch normalization to the best performing ImageNet classification network and show that we can match its performance using only 7% of the training steps and can further exceed its accuracy by a substantial margin. Using an ensemble of such networks trained with batch normalization, we achieve the top 5 error rate that improves upon the best known results on ImageNet classification. 2. Towards reducing internal covariance shift. We define internal covariance shift as the change in the distribution of network activations due to the change in network parameters during training. Change in distribution of network activations due to the change in network parameters during training. To improve the training, we seek to reduce the internal covariance shift. And, I wonder if it would be, in that case, if it would be valuable. I was thinking about this while working on the statistics object today. I wonder if it would be valuable to actually track all of the activations associated with each training sample, to map how those, to actually check activation by activation and track how they change for each sample. Of course, that amount of data would probably be infeasible for larger models, but for the toy models I'm working with, it's at least measurable. I don't know if it's useful information, but I guess it's something to look at. Let's see. Activation statistics. Oh, you know what? I was just thinking about how I'm going to implement all these different statistics holders, and I just realized each one can be specialized for a specific, data type, to avoid redundancy, and those can be reused with the decorator pattern if we allow. I guess we could have like a top-level aggregate statistic object that allows multiple statistics children that it delegates the behavior to for every call. So, each one of them can track statistics individually with whatever they're interested in. That seems... it's an idea, at least. So, activation statistics, let's see, is that on my list? Yes, I do have activations. Okay. So yeah, we would want to track not just activations, but activations associated with specific samples. Gosh, passing all that data for every single call. That's not bad. Whatever, I'll put that on side burner. Okay. In section 4.2, we apply batch normalization to the best performing ImageNet classification network and show that we can match its performance using only 7% of the training steps and can further exceed its accuracy by a substantial margin. Using an ensemble of such networks trained with batch normalization, we achieve the top 5 error rate that improves upon the best known results on ImageNet classification. I already read that part. Whoops. And fixing the distribution of training, we seek to reduce info covariance shift. By fixing the distribution of the layer inputs X as the training progresses, we expect to improve the training speed. It has been long known, LeCun et al. 1998, wow, Weissler in 2011, that the network training converges faster if its inputs are whitened, i.e. linearly transformed to have zero means and unit variances and decorrelated. Huh. It has been long known that the network training converges faster. Now, is that tested empirically or is that actually proven analytically? So I guess that's prior work to look at. Let's see. Yeah. Training converges faster if its inputs are whitened. Faster. Whitened. Linearly transformed to have zero means and unit variances and decorrelated. As such, as each layer observes the inputs produced by the layers below, it would be advantageous to achieve the same whitening of the inputs of each layer. By whitening the inputs to each layer, we would take a step towards achieving the fixed distributions of inputs that would remove the ill effects of the internal covariate shift. We could consider whitening activations at every training step, or at least some internal interval, either by modifying the network directly or by changing the parameters of the optimization algorithm to depend on the network activation values. By modifying the network directly or by changing the parameters of the optimization algorithm to depend on the network activation values. However, if these modifications are interspersed with the optimization steps, then the gradient descent step may attempt to update the parameters in a way that requires the normalization to be updated, which reduces the effect of the gradient step. For example, consider the parameters that requires the normalization to be updated, which reduces the effect of the gradient step. For example, consider a layer with the input U that adds the learned bias B and normalizes the result by subtracting the mean of the activation computed over the training data. So x hat equals x minus expectation value of x, where x equals u plus b, and the set x equals x1, the training data x1 to n is the set of values of x over the training set, and expectation value of x equals the average over the set of values of x. If a gradient descent step ignores the dependence of expectation value of x on b, then it will update b as b plus delta b, where delta b is proportional to negative partial derivative of loss with respect to x hat. Then u plus b plus delta b minus the expectation value of u plus b plus delta b equals u plus b minus expectation value of u plus b. Thus, the combination of the update to b and subsequent change in normalization led to no change in the output of the layer, nor, consequently, the loss. As the training continues, b will grow indefinitely while the loss remains fixed. This problem can get worse if the normalization not only centers but also scales the activations. We have observed this empirically in initial experiments where the model blows up when the normalization parameters are computed outside the gradient descent step. The issue with the above approach is that the gradient descent optimization does not take into account the fact that the normalization takes place. To address this issue, we would like to ensure that for any parameter values, the network always produces activations with the desired distribution. Doing so would allow the gradient of the loss with respect to the model parameters to account for the normalization and force dependence on the model parameters theta. Let again x be a layer input treated as a vector and x be the set of these inputs over the training data set. The normalization can then be written as a transformation. X hat equals norm of x, set of x, which depends not only on the given training example x, but on all examples x, each of which depends on theta if x is generated by another layer. For backpropagation, we would need to compute the Jacobians, the partial derivative of norm of x and the set x with respect to x, and the partial derivative norm of x, the set of x, with respect to the set x. Ignoring the latter term would lead to the explosion described above. Within this framework, whitening the layer inputs is expensive as it requires computing the covariance matrix. Covariance x equals, oh my goodness, expectation for that. X member of the set X of x times x transpose minus expectation value of x times expectation value of x transpose, and its inverse square root to produce the whitened activation's covariance, oh my goodness, of x power minus half of x minus expectation of x, as well as the derivatives of these transforms for backpropagation. This motivates us to seek an alternative that performs input normalization in a way that is differentiable and does not require the analysis of the entire training set after every parameter update. Some of the previous approaches, e.g. Liu and Simoncelli, 2008, use statistics computed over a single training example, or in the case of image networks, over different feature maps at a given location. However, this changes the representation ability of the network by discarding the absolute scale of activations. We want to preserve the information in the network by normalizing the activations in a training example relative to the statistics of the entire training data. Normalization via mini-batch statistics. Oh. Since full whitening of each layer's inputs is costly and not everywhere differentiable, we make two necessary simplifications. The first is that instead of whitening the features and layer inputs and outputs jointly, we will normalize each scalar feature independently by making it have mean of 0 and the variance of 1. For a layer with d-dimensional input, x equals x1 to xd, we will normalize each dimension. The expectation and variance are computed over the training dataset. As shown in LeCun, such normalization speeds up convergence even when the features are not decorrelated. Note that simply normalizing each input of a layer may change what the layer can represent. For instance, normalizing the inputs of a sigmoid would constrain them to the linear regime of the nonlinearity. To address this, we make sure that the transformation inserted in the network can represent the identity transform. To accomplish this, we introduce for each activation x to the power k a pair of parameters gamma to the power k and beta to the power k, which scale and shift the normalized value. Oh, that's not power, that's supposed to be the index issue. These parameters are learned along with the original model parameters and restore the representation power of the network. Indeed, by setting gamma k equals square root variance of xk and beta k equals expectation value of xk, we could recover the original activations if that were the optimal thing to do. In the batch setting, where each training step is based on the entire training set, we would use the whole set to normalize activations. However, this is impractical when using stochastic optimization. Therefore, we make the second simplification. Since we use mini batches in stochastic gradient training, each mini batch produces estimates of the mean and variance of each activation. This way, the statistics used for the normalization can fully participate in the gradient backpropagation. Note that the use of mini batches is enabled by computation of per-dimensional variances rather than joint covariances. In the joint case, regularization would be required since the mini batch size is likely to be smaller than the number of activations being whitened, resulting in singular covariance matrices. Consider a mini batch beta of size m. Since the normalization is applied to each activation independently, let us focus on a particular activation xk and omit k for clarity. We have m values of this activation in the mini batch. Okay, so batch equals x1 to m. Let the normalized values be x hat 1 to m and their linear transformations be y1 to m. We refer to the transform batch normalization gamma beta x1m maps to y1 to m as the batch normalizing transform. We present the batch normalizing transform in algorithm 1, and the algorithm epsilon is a constant add to the mini batch variance for numerical stability. Yeah. Ugh. To avoid division by 0. Input values of x over a mini batch. Parameters to be learned, gamma, beta. Output. Uh, okay. Let's see. Activation X for a mini batch. Okay, so let's see. Values of X over a mini batch. Batch parameters to be learned. Gamma beta. One batch normalizing transform applied to activation X over mini batch. So mini batch mean, mini batch variance, normalize. Yeah, so you just calculate the mean and the variance. Normalize like you would for a statistical distribution. Subtract by the mean, divide by the square root of the variance. Scale and shift. So X hat, X. Batch normalizing transform applied to activation X over mini batch. Batch normalizing transform can be added to a network to manipulate any activation. In the notation y equals batch norm, what do we do? We indicate that the parameters gamma and beta are to be learned, but it should be noted that batch normalizing transform does not independently process the activation in each training example. Rather, batch norm gamma beta x depends both on the training example and the other examples in the mini batch. Scaled and shifted values y are passed to other network layers. The normalized activations x hat are internal to our transformation, but their presence is crucial. The distributions of values of any x hat has to be expected values of 0 and the variance of 1, as long as the elements of each mini batch are sampled from the same distribution, and if we neglect epsilon. This can be seen by observing that the sum over m of xi hat equals 0 and 1 over m equals 1. In taking expectations, each normalized activation x hat k can be viewed as an input to the subnetwork composed of the linear transform yk equals gamma k times x hat k plus beta k, followed by the other processing done by the original network. These subnetwork inputs all have fixed means and variances, and although the joint distribution of these normalized x hat k change over the course of training, we expect that the introduction of normalized inputs accelerates the training of the subnetwork and consequently the network as a whole. During training, we need to backpropagate the gradient of loss L through this transformation, as well as compute the gradients with respect to the parameters of the batch norm transform. We use chain rule as follows before simplification. During training, we need to backpropagate the gradients of loss L through this transformation, as well as compute the gradients with respect to the parameters of the batch norm transform. We use chain rule as follows before simplification. Thus, batch norm transform is a differentiable information that introduces normalized activations into the network. This ensures that as the model is training, layers can continue learning on input distributions that exhibit less internal covariate shift, thus accelerating the training. Furthermore, the learned affine transform applied to these normalized activations allows the batch norm transform to represent the identity transformation and preserves the network capacity. Training and inference with batch normalized networks. To batch normalize a network, we specify a subset of activations and insert the batch norm transform for each of them, according to algorithm 1. Any layer that previously received X as the input now receives batch norm X. A model employing batch normalization can be trained using batch gradient descent or stochastic gradient descent with bending batch size m greater than 1, or with any of the variants, such as attgrad. The normalization of activations that depends on the many batch allows efficient training, but is neither necessary nor desirable during inference. We want the output to depend only on the input deterministically. For this, once the network has been trained, we use the normalization. X hat equals X minus expectation value X all over variance of X plus epsilon all over square root of variance X plus epsilon. Using the population rather than mini-batch statistics, neglecting epsilon, these normalized activations have the same mean 0 and variance 1 as during training. We use the unbiased variance estimate. Variance X equals m over m minus 1 times expectation value of the batch with respect to batch of sigma 2 sigma squared. It's supposed to be the sigmoid output, where the expectation is overtraining many batch size m and sigmoid 2 are their simple. Okay, so it's not the sigmoid function, it's traditional statistical sigmoid, so variance. Using moving averages instead, we can track the accuracy of a model as it trains. Since the means and variances are fixed during inference, the normalization is simply a linear transform applied to each activation. It may further be composed with the scaling by gamma and shift by beta to yield a single linear transform that replaces batch norm X. Our algorithm 2 summarizes the procedure for training batch normalized networks. Network N with trainable parameters theta, subset of activations xk, k equals 1, or set k. Batch normalized network for inference. In inference and batch norm. In training batch norm. Assigned to N training batch norm network. Ah, interesting. That's an interesting way to do it. Huh. Wow, they're copying the entire network. I guess that makes sense if you need to refer to the activations weights between generations. Hmm. Thus, batch norm transform is a differentiable transformation that introduces normalized activations into the network. This ensures that as models training layers can continue to learn. Already read all that. So looking at the second algorithm, algorithm 2, training a batch normalized network. For k equals 1 to k, do add transformation yk equals batch norm gamma k beta k of xk, excuse me, 2. Network training. Modify each layer in the training batch network with input xk to take yk instead. And do that for each k. Train batch norm training network to optimize the parameters theta union gamma k beta k, and then we the inference network, batch norm inference network, is assigned the batch norm training network inference batch network with frozen parameters. For k equals 1 to k, do for clarity x is exactly equal to xk, gamma is exactly like yk, mu beta is exactly equal to mu beta k, etc. Process multiple training mini batches, beta batch, each of size m, and average over them. Expectation value of x is assigned expectation value of batch of mu batch, the mean of the batch. And then variance of x is assigned m over m minus 1 times expectation value of the variance of the batch in oh, that's right, because yeah, standard deviation is the square root of that, and variance is the square root of variance. And variance is the squared quantity. Basics. In the inference batch network, replace the transform y equals batch norm with y equals gamma over square root variance 1 times x plus oh my Whew. Mm. Hmm. Training and inference with batch normalized networks. To batch normalize the network, we specify a subset of activations and insert the batch norm transform for each of them, according to algorithm 1. Any layer that previously received x as the input now receives batch norm x. A model employing batch normalization can be trained using batch gradient descent, or stochastic gradient descent, with a mini batch size m greater than 1, or with any of its variants such as adgrad. The normalization of activations that depends on the mini batch allows efficient training, but is neither necessary nor desirable during inference. We want the output to depend only on the input, deterministically. For this, once the network has been trained, we use the normalization x hat equals x minus expectation value of x all over square root variance of x plus epsilon, using the population rather than mini batch statistics. Oh, I've already read that. Ugh, I'm reading it. Batch normalization can be applied to any set of activations in the network. Here we focus. Oh, that's important to know. Any set of activations in the network. Here we focus on transforms that consist of an affine transformation followed by an element-wise nonlinearity. C equals G times W plus B, where W and B are learned parameters of the model, and G is a nonlinearity such as sigmoid or ReLU. This formulation covers both fully connected and convolutional layers. We add the batch norm transform immediately before the nonlinearity. Oh, we add the batch transform immediately before the nonlinearity by normalizing x equals WU plus B, x equals WU plus B. We could have also normalized layer inputs U, but since U is likely the output of another nonlinearity, The shape of its distribution is likely to change during training, and constraining its first and second moments would not eliminate the covariant shift. In contrast, W times U plus B is more likely to have a symmetric, non-sparse distribution, that is, more Gaussian. Normalizing, it is likely to produce activations with a stable distribution. Note that since we normalize WU plus B, the bias B can be ignored since its effect will be cancelled by the subsequent mean subtraction. The role of the bias is subsumed by beta in algorithm 1. Thus, Z equals G times W plus B is replaced with Z equals G of batch norm of W. The batch norm transform is applied independently to each dimension of X equals W, with a separate pair of learned parameters, gamma k, beta k per dimension. For convolutional layers, we additionally want the normalization to obey the convolutional properties so that different elements of the same feature map at different locations are normalized in the same way. To achieve this, we jointly normalize all the activations in a mini-batch over all locations. In algorithm 1, we let beta be the set of all values in a feature map across both elements of a mini-batch and spatial locations. So for a mini-batch of size M and feature maps of size P cross Q, we use the effective mini-batch of size M prime equals magnitude of B equals M times PQ. We learn a pair of parameters, gamma k and beta k, per feature map rather than per activation. Algorithm 2 is modified similarly so that during inference, the batch norm transform applies the same linear transformation to each activation in a given feature map. Batch normalization enables higher learning rates. In traditional deep networks, too high learning rate may result in the gradients that explode or vanish, as well as getting stuck in poor local minima. Batch normalization helps address these issues. By normalizing activation throughout the network, it prevents small changes to the parameters from amplifying into larger and suboptimal changes in activations and gradients. For instance, it prevents the training from getting stuck in the saturated regimes of nonlinearities. Batch normalization also makes training more resilient to the parameter scale. Normally, large learning rates may increase the scale of the layer parameters, which then amplify the gradient during backpropagation and lead to the model explosion. However, with batch normalization, backpropagation through a layer is unaffected by the scale of its parameters. Indeed, for a scale alpha, batch norm of W times U equals batch norm of A times W times U. Yeah, and we can show that batch norm equals batch norm derivative to 1 over A times batch norm U. Scale does not affect the layer Jacobian nor, consequently, the gradient propagation. Moreover, larger weights lead to smaller gradients, and batch normalization will stabilize the parameter growth. We further conjecture that batch normalization may lead the layer Jacobians to have singular values close to 1, which is known to be beneficial for training. That's interesting. Further conjecture that batch normalization may lead the layer Jacobians to have singular values close to 1, which is known to be beneficial for training. Consider two consecutive layers with normalized inputs and the transformation between these normalized vectors. Consider two consecutive layers with normalized inputs and the transformation between these normalized vectors, z and f of x. Assume that x and z are Gaussian and uncorrelated, and that f of x is proportional to jx is a linear transformation for the given model parameters. Then both x and z have unit covariances, and I equals covariance of z equals j times covariance x times j transpose equals j times j transpose. Thus, j times j transpose equals I. And so all singular values of j are equal to 1. Which preserves the gradient magnitudes during backpropagation. Wait. This is a great piece of information for my hypothesis. It's j times j transpose I, and so all singular values of j are equal to 1, which preserves the gradient magnitudes during backpropagation. That was the whole idea. In reality, the transformation is not linear, and the normalized values are not guaranteed to be Gaussian nor independent, but we nevertheless expect batch normalization to help make gradient backpropagation better behaved. The precise effect of batch normalization on gradient propagation remains an area of further study. If we assume that x and z are Gaussian and uncorrelated, and that f of x hat is approximate to j times x hat, linear transformation of the given model parameters, then both x hat and z hat have unit covariances, and I equals covariance of z hat equals j times covariance of x hat times j transpose. In reality, batch normalization regularizes the model. When training with batch normalization, a training example is seen in conjunction with other examples in the mini-batch, and the training network no longer produces deterministic values for a given training example. In our experiments, we found this effect to be advantageous to the generalization of the network. Whereas dropout is typically used to reduce overfitting, in a batch normalized network, we found that it can be either removed or reduced in strength. Experiments. 4.1 activations over time. To verify the effects of internal covariance shift on training and the ability of batch normalization to combat it, we consider the problem of predicting the digit class on the MNIST dataset. We used a very simple network with a 28 by 28 binary image as input. And 3 fully connected hidden layers with 100 activations each. Each hidden layer computes, actually, doesn't seem like too large of a network. It's a very simple network, yeah, for MNIST. Training and ability batch normalization to combat it, we consider problem digit class on MNIST. It's a very simple network, 28 by 28 binary image input. And 3 fully connected hidden layers with 100 activations each. Each hidden layer computes y equals g w plus b with sigmoid nonlinearity, and the weights w initialized to small random Gaussian values. Last hidden layer is followed by a fully connected layer with 10 activations, 1 per class, and cross entropy loss. We train the network for 50,000 steps with 60 examples per mini batch. 50,000 steps, 60 examples per mini batch. We added batch normalization to each hidden layer of the network, as in section 3.1. We are interested in the comparison between the baseline and batch normalized networks, rather than achieving the state-of-the-art performance on MNIST, which the described architecture does not. Figure 1a shows the fraction of correct predictions by the two networks on held-out test data as training progresses. The batch normalized network enjoys the higher test accuracy. To investigate why, we study inputs to the sigmoid in the original network N in batch normalized network 2 over the course of training. In figure 1, we show for one typical activation from the last hidden layer of each network, now its distribution evolves. The distributions in the original network change significantly over time, both in their mean and the variance, which complicates the training of the subsequent layers. In contrast, the distributions in the batch normalized network are much more stable as training progresses, which aids the training. 4.2 ImageNet classification. We applied batch normalization to a new variant of the inception network. Trained on the ImageNet classification task, the network has a large number of convolutional pooling layers with softmax layer to predict the image class out of 1,000 possibilities. Convolutional layers use ReLU as the nonlinearity. The main difference to the network described in SysD is that 5 by 5 convolutional layers are replaced by 2 consecutive layers of 3 by 3 convolutions with up to 128 filters. The network contains 13.6 times 10 to the 6 parameters, and other than the top softmax layer, has no full connect layers. More details are given in the appendix. We refer to this model as inception in the rest of the text. The model was trained using a version of stochastic gradient descent. Inception is another paper I need to print off. The model was trained using a version of stochastic gradient descent with momentum using the mini batch size of 32. The training was performed using a large-scale distributed architecture, similar to Dean et al. 2012. All networks are evaluated as training progresses by computing the validity accuracy at 1, i.e., the probability of predicting the correct label out of 1,000 possibilities on a held-out set using a single crop per image. In our experiments, we evaluated several modifications of inception with batch normalization. In all cases, batch normalization was applied to the input of each nonlinearity in a convolutional way, as described in section 3.2, while keeping the rest of the architecture constant. Accelerating batch norm networks. Simply adding batch normalization to a network does not take full advantage of our method. To do so, we further change the network and its training parameters as follows. Increase learning rate. In a batch normalized model, we have been able to achieve a training speedup from higher learning rates with no ill side effects. Remove dropout. As described in section 3.4, batch normalization fulfills some of the same goals as dropout. Removing dropout from modified batch norm inception speeds up training without increasing overfitting. So the same goes as dropout. Reduce the L2 weight regularization while in inception, an L2 loss on the model parameters controls overfitting. In modified batch norm inception, the weight of the loss is reduced by a factor of 5. We find that this improves the accuracy of the held out validation data. Accelerate the learning rate decay. In training inception, learning rate was decayed exponentially. Because our network trains faster than inception, we lower the learning rate 6 times faster. Remove local response normalization. While inception and other networks benefit from it, we found that with batch normalization, it's not necessary. Shuffle training examples more thoroughly. We enabled within shard shuffling of the training data, which prevents shuffle training data example more thoroughly. Within shard shuffling of the training data, which prevents the same examples from always appearing in a manner batch together. This led to about 1% improvements in the validation accuracy, which is consistent with the view of batch normalization as a regularizer. Randomization inherent in our method should be most beneficial when it affects an example differently each time it is seen. Reduce the photometric distortions. Because batch normalized networks train faster and observe each training example fewer times, we let the trainer focus on more real images by distorting them less. Interesting. I guess that's to artificially expand the distribution of the training data to hopefully encompass more test data. Single crop validation accuracy of inception and its batch normalized variance versus the number of training steps. Okay, so let's see. Inception looks like the first one, and then batch norm baseline, and batch norm times 5, batch norm times 30, batch norm times 5 sigmoid, steps to match inception. Oh, wow. Wow. That is a lot faster. Holy hell. From 30 million steps to maybe 3 million. Or it looks more like 2. The network described at the beginning of section 4.2 trained with the initial learning rate of 0.0015 batch norm baseline, same as inception with batch normalization before each linearity. Batch norm times 5, inception with batch normalization. Let's see what the batch norm baseline. Yeah, so just the baseline, just batch norm alone, it like takes half the training time. Batch norm times 5, inception with batch normalization, and the modifications in section 4.2.1, the initial learning rate was increased by a factor of 5 to 0.0075. The same learning rate increase with the original inception caused the model parameters to reach machine infinity. Same learning rate with original inception caused, oh yeah, Batch norm times 3 times 3. Like batch norm times 5, but with the initial learning rate 0.045, 30 times that of inception. Man. And it reaches a higher overall accuracy. Batch norm times 5 sigmoid, like batch norm times 5, but with sigmoid non-linearity, GT, instead of ReLU. We also attempted to train the original inception with sigmoid, but the model remained at the accuracy equivalent to chance. Interesting. In figure 2, we show the validation accuracy of the networks. As a function of the number of training steps, inception reached the accuracy of 72.2 after 31 times 10 to the 6 training steps. Yeah. Figure 3 shows that for each network, the number of training steps required to reach the same 72.2 accuracy as was the maximum validation accuracy reached by the network and the number of steps to reach it. By only using batch normalization, we match the accuracy of inception in less than half the number of training steps. By applying the modifications in section 4.2.1, we significantly increase the training speed of the network. Batch norm times 5 needs 14 times fewer steps than inception to reach 70.2 accuracy. Interestingly, increasing learning rate further, batch norm times 30, causes the model to train somewhat slower initially, but allows it to reach a higher final accuracy. It reaches 70.48% after 6 times 10 to the 6 steps, i.e. 5 times fewer steps than required by inception to reach 70.2. We also verified that the reduction in internal covariate shift allows deep networks with batch normalization to be trained when sigmoid is used as the nonlinearity, despite the well-known difficulty of training such networks. Indeed, batch norm times 5 sigmoid achieves the accuracy of 69.8% without batch normalization. Inception with sigmoid never achieves better than 1/1000th accuracy. Interesting. Hmm. Hmm. Ensemble classification. The current reported best results on the ImageNet large-scale vision recognition competition are reached by the deep image ensemble of traditional models. And the ensemble model of the latter reports the top 5 error of 4.94 as evaluated by the ILS-VRC server. Here we report a top 5 validation error of 4.9% and test error of 4.82%. According to the ILS-VRC server, this improves upon the previous best result and exceeds the estimated accuracy of human raters according to Tchaikovsky et al. For our ensemble, we used 6 networks. Each was based on batch norm times 30 modified via some of the following. Increased initial weights in the convolutional layers, using dropout with a dropout probability of 5% or 10% versus 40% for the original inception, and using non-convolutional per activation batch normalization with last hidden layers of the model. Each network achieved its maximum accuracy after about 6 times 10 to the 6 training steps. The ensemble prediction was based on the arithmetic average of class probabilities predicted by the constituent networks. The details of ensemble and multi-crop inference are similar to Szilagyi et al. We demonstrate in Figure 4 that batch normalization allows us to set new state-of-the-art by a healthy margin on the ImageNet classification challenge benchmarks. Conclusion, we have presented a novel mechanism for dramatically accelerating the training of deep networks. It is based on the premise that covariate shift, which is known to complicate the training of machine learning systems, also applies to subnetworks and layers. And removing it from internal activations of the network may aid in training. Our proposed method draws its power from normalizing activations and from incorporating this normalization in the network architecture itself. This ensures that the normalization is appropriately handled by any optimization method that is being used to train the network. To enable stochastic optimization methods commonly used in deep network training, we perform the normalization for each mini-batch and backpropagate the gradients through normalization parameters. Batch normalization adds only 2 extra parameters per activation, and in doing so preserves the representation ability of the network. We presented an algorithm for constructing, training, and performing inference with batch normalized networks. The resulting networks can be trained with saturating nonlinearities, are more tolerant to increased training rates, and often do not require dropout for regularization. Merely adding batch normalization to a state-of-the-art image classification model yields a substantial speedup in training. By further increasing the learning rates, removing dropout, and applying other modifications afforded by batch normalization, we reach the previous state-of-the-art with only a small fraction of training steps, and then beat the state-of-the-art in single network image classification. Furthermore, by combining multiple models trained with batch normalization, we perform better than the best-known system on ImageNet by a significant margin. Interestingly, our method bears similarity to the standardization layer of and Bingio. But the two methods stem from very different goals and perform different tasks. The goal of batch normalization is to achieve a stable distribution of activation values throughout training, and in our experiments we apply it before the nonlinearity, since that is where matching this first and second moments is more likely to result in a stable distribution. On the contrary, apply the standardization layer to the output of the nonlinearity, which results in sparse activations. In our large-scale image classification experiments, we have not observed the nonlinearity inputs to be sparse, neither with nor without batch normalization. Other notable differentiating characteristics of batch normalization include the learned scale and shift that allow the batch norm transform to represent identity. The standardization layer did not require this since it was followed by the learned linear transform that conceptually absorbs the necessary scale and shift. Handling of convolutional layers, deterministic inference that does not depend on the mini-batch, and batch normalizing each convolutional layer in the network. In this work, we have not explored the full range of possibilities that batch normalization potentially enables. Our future work includes applications of our method to recurrent neural networks, where the internal covariate shift in the vanishing or exploding gradients may be especially severe, and which would allow us to more thoroughly test the hypothesis that normalization improves gradient propagation. We plan to investigate whether batch normalization can help with domain adaptation in its traditional sense, i.e., whether normalization performed by the network would allow it to more easily generalize to new data distributions, perhaps with just a recomputation of the population means and variances. Finally, we believe that further theoretical analysis of the algorithm would allow still more improvements and applications. Indices. Variant of the inception model used figure 5 documents the changes that were performed compared to the architecture with respect to Google Net architecture. For the interpretation of the table, please consult Syzygy et al. The notable architecture changes compared to the Google Net model include the 5x5 convolution layers are replaced with 2 consecutive 3x3 convolution layers. This increases the maximum depth of the network by 9 weight layers. Also increases the number of parameters by 25%, and the computational cost is increased by about 30%. The number 28 by 28 inception modules is increased from 2 to 3. Inside the modules, sometimes average, sometimes maximum pooling is employed. This is indicated in the entries corresponding to the pooling layers of the table. There are no across-the-board pooling layers between any 2 inception modules, but stride 2 convolution pooling layers are employed before the filter concatenation of the modules 3C, 4E. Our model employed separable convolution with depth multiplier 8 on the first convolutional layer. This reduces the computational cost while increasing the memory consumption at training time. Exception 3A, 3B, 3C, 4A, 4B, 4C, 4D, 4E, 5A, 5B. Inception architecture. 3x3 reduce, double 3x3 reduce, double 3x3 pull in projection. Batch size, stride, output size, depth. Okay. Alright. I have to read that one again, just to make sure I really understand it. And, of course, I'll have to read it when I implement it, so. Yeah, back to statistics. Okay.